All right, this is Honors Algebra 2 Pre-Calculus. We are working on 6.2 in Algebra 2, which is exponential functions. So consider the function y equals x squared versus y equals 2x, right? So both functions have a base, and both functions have an exponent. However, y equals x squared is what's called quadratic, right? And y equals 2x is what's called exponential. The difference here is that in an exponential function, the base is a fixed number and the exponent is the variable. So the function f of x equals b raised to the x is an exponential function with base b, where b is a positive real number that is not 1, and x is any real number, right? So we have a base and an exponent, and we saw in the last video that sometimes we see this written where there's another value in front, like this a times b to the x, right? This would still be the base, right? What would make this different is that this is an initial value, right? So it's an initial value. We saw that with bacteria populations where the A was a 100. Okay, so moving on. So let's look at this table, right? So we have a table and a graph, right? So this table for an exponential function, y equals 2 to the x, and this is the graph for y equals 2 to the x. Notice that as the x values decrease for y equals 2 to the x, the graph gets closer and closer to 0, right? So what this is called, right? So this line right here, see how the graph is approaching this. This is called an asymptote. Okay, you don't say asymptote you don't say the p very hard, but it is asymptote. So we're going to spend a lot of time in 8.2 of Algebra 2. We're going to spend a lot of time learning more about asymptotes. But essentially, an asymptote is a line that a graph approaches as very, very infinitely close to. So it's sort of like a fence that a graph approaches and runs along. So this graph is going to run right next to that axis. But one thing I want you to notice is that y equals 2 to the x is well, it's positive. I don't even have to say non-negative, right? It's never 0. So it's always going to be positive. It's going to get really, really small, but it's never 0. It approaches 0, but it's never actually 0, right? So just to give you a heads up about how that works, right? So if we were talking, in a second we're going to talk a little bit about the domain and the range of these graphs. But again, this is an asymptote. It's a line that the graph approaches and gets very, very close to, but doesn't actually reach, okay? So let's look at the graph of f of x equals 2 to the x versus g of x equals 1/2 raised to the x. So these exhibit the two typical behaviors that we're going to see in exponential functions a lot. So f of x equals 2 to the x is what we call exponential growth. Oh, it's right there. Sorry, my bad. Exponential growth, right? So exponential growth where we start with very small values and then it explodes up, exponential growth, right? G of x is exponential decay, where we start with really big values and it cuts down, way down until it approaches this idea of approaching 0, right? So let's look at domain and range of these functions, right? So domain and range of these functions, so for E, right? So you can see that for F, you can see that there are arrows going left and right forever. So the domain of, so remember my f of x was a 2 to the x, right? My domain is all real numbers. I can write that as negative infinity to infinity. I can write it as all real numbers, however you want to write it, right? My range, however, is going to get close to but never reach 0. So I'm going to put a parenthesis next to the 0, and it's going to go up forever, right? So that's my domain and range for f. For g of x, you'll see that the same thing happens. It just kind of happens in the opposite order, right? You'll see that this goes left and right forever. So my domain is negative infinity to infinity, and my range, again, it approaches this 0 but never reaches it, so it's going to be 0 to infinity. Okay, that's our domain and range for exponential functions. All right, so one side note, right? So if you think back to 2.7, it actually makes a lot of sense that if we look at these two graphs, right, essentially we could treat these two graphs like they are flipping over the y-axis, right? And that makes a lot of sense if you look at it. If you reflect the blue graph over the y-axis, you get the red graph. Well, that makes a lot of sense because if you think about f of x being 2 to the x, right, f of negative x is a flip over the y-axis, right? Well, f of negative x would be 2 to the negative x, which is the same as a essentially a 2 to the negative 1 to the x, or a 1/2 to the x, which is definitely what our g of x was, right? So it makes sense that when you look at these two graphs, right, here's my y-axis, f of x looked like this, and g of x looked like I flipped this thing over this axis, which would be this. Oh, hey, there's my g of x, right? So it's actually not an accident that that's true. It's just a different way to write it. So so notice that 2 to the negative x is the same as 1/2 raised to the x, and they're both decay, right? So we addressed this in the last video, which is that when b is greater than 1, we're looking at exponential growth, right? That was that multiplier that's bigger than 1. And when b is between 0 and 1, we're looking at exponential decay. We did actually talk about that in 6.1. All right, so we're going to graph both of these functions and indicate if the function is exponential growth or decay. So I'm fine with you graphing this on a calculator. You don't have to graph it by hand. You could graph it by hand. I don't really care. What I will say is if you choose to graph it by hand, you should pick nice, easy values for your table. So I'm going to show you what happens if I graph by hand. So I'm going to pick the nice, easy values I'm going to pick for my table. For my x's are -2, -1, 0, 1, and 2. Right, and my f of x is going to be a 2 times this 3 to the x, right? So if I pick this, right, so when I pick a -2, this is going to be a 2 times a 3 to the -2nd, which is a 2 times 1/9, or 2/9, right? This is going to be a 2 times a 3 to the -1st, which is a 2 times a 3rd, so 2/3. This is going to be a 2 times a 3 to the 0, which is just a 2. It's going to be a 2 times a 3 to the 1st, which is a 6. This is going to be a 2 times a 3 squared, which is a 2 times 9, or an 18. So if I were to graph this by hand, and again, you don't have to, right? But if I were going to graph this by hand, I don't need any negative y values, right? But I need some pretty big x values. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Hey, I just made it to 18. Okay, so 2/9 is 0.2 repeating, but honestly, for my purposes, it's just really close to 0 because look how big this graph is. 2/3 is slightly farther from 0, right? And then I get to a 2, and then a 6, and then this thing explodes all the way up to an 18. So there's my A graph, right? So it's my f of x, right? And if I want to do my g of x, right? So I could probably arguably even just squeeze the table next to it, but we're going to make it work. So so here's my x. We'll do -2, -1, and my g of x is a 2 times a 3 to the -x. I'm just going to keep making this table go over here because I don't really feel like having to rewrite all of this. We're going to squeeze it in. Okay, so my g of x is a 2, 3 to the -x. All right, cool. So when I plug in -2, I'm going to get 2, 3 to the 2nd. Well, oh, hey, that's that 18 that we saw right here. So that's actually going to be here, not shocked, right? This is going to be a 2 times a 3 to the regular 1. Well, that's the 6 that we already saw. That's this point, but it's over here, right? 2 times a 3 to the 0 is still a 2. Well, that's the same point here. 2 times a 3 to the -1st is that 2/3 that we've already seen, which is here, give or take. And then 2 times a 3 to the -2nd is a 2/9, which again is this point, but on this side. So it's not at all surprising. Essentially, this is what would happen if I flipped my f of x over the y-axis. So g of x is decay, right? And f of x was growth. And the other way to see that g of x is decay is your multiplier is actually a 1/3, right? Because a 3 to the -x is the same as a 1/3 to the positive x. All right, if you go ahead and give P1 a try, right? Again, you can do it by hand, you can do it on a calculator. I don't really have a strong preference. I just want you to give it a try. So I'm going to go ahead and make my table for A. Again, the easy x values to pick are -2, -1, 0, 1, and 2. And honestly, if you want, you could probably just make this table have both of them, right? You could make this have f and g, so you could just not even call it A. You could say, hey, look, I'm just going to do this. It's easier. It's totally fine. All right, if you plug a -2 in, you're going to get a 1/4 times 2 to the -2nd is another 1/4. So you're going to get a 1/16. If you plug a -1 in, you're going to get a 1/4 times a 2 to the -1st, which is a half. So that's a 1/8. If you plug a 0 in, you're going to get a 1/4 times a 2 to the 0, which is 1/4 times 1, so just a fourth. If you plug in a 1, you're going to get 1/4 times a 2 to the first, so that's a 1/2. And if you plug in a 2, you're going to get a 1/4 times a 4, which is a 1. So those are all pretty small values, right? If you do the same thing on the other side, you're basically going to see that you get exactly the opposite order of the values, right? Because this is going to be a 1/4 times a 2 to the second. Oh, look, that's a 1, which we saw right here. The same thing's going to happen here. This is going to be a 1/4 times a 2 to the negative 1 times negative, which is a positive 1. So, oh, look, there's the 0.5 or the 1/2. There's that one, right? This one's still going to be a fourth. This one's still going to be a 1/8. And this one's going to be a 1/16. So they're basically in the opposite order, right? So if you were graphing this, now you don't need those giant y values, right? The biggest y value you seem to need is 1, right? So that's 1/2, makes that a fourth, makes that 3/4, right? So I needed much smaller values, right? So let's go ahead and do f in green here, right? So I'm going to start at 1/16. Well, 1/16 is a quarter of a fourth. That's pretty small, right? 1/8 is a half of a fourth. This is a fourth. Then a half, and then 1. So we get a graph that looks like this, right? That's my f, which is definitely growth. And then if I do this one in blue, that's going to be decay. And I can see that because literally the opposite points, right? The 1 was over here, now the 1's here. The 1/2 was here, now it's here. The 1/4 stays the same. And so I get my decay. And again, you can graph it on a calculator, but you should be able to graph a basic growth and decay graph